Okay, I'm sure that was quite confusing, so let's do some more concrete examples here. We'll just start with force. We'll put our force here, and we'll put Z here and mu here. It's a very crude diagram, but this is what we're talking about. And we know classically that force over mu is velocity squared, and that's well established. But from the rules we just saw, force times mu is actually impedance squared. This is a very interesting result. Another example is to suppose we were to start in power here, force here, and impedance here, and we can state this: power over impedance is velocity squared, and also power times impedance is force squared.
Okay, indeed.
We can go for another example with energy, force, decay, and we write energy over K equals x squared energy times K equals force squared. So any pair of boxes that are oppositely arranged, you can make these remarks about. There's other interesting interpretations now that we will look at. We've already seen that if you're in this box and you're want to know what's in this box, we know that it's the integral dx. And so if you look at a derivation and you see them doing an integral dx, you can think that you can realize that they are talking about the box above whatever they're integrating. We can do, well, if we look at the Euler-Lagrange equation here now, this is a rather complicated subject. It says that the partial with respect to x of Lagrangian function is equal to the time derivative of the partial with respect to v of the Lagrangian function. What does all this mean or say? Well, what is the Lagrangian function? It's an energy expression. It's kinetic energy minus potential. So it's an energy expression. And so we can now look at our left side of our equation, partial with respect to x of energy. Start in energy and take the partial derivative, that takes us to force. So this is a force expression. And it's, in particular, this expression is describing one way to get from the energy box to the force box. Now if we look at the right side, we'll have to unwrap that. It has a ddt, and then what's inside is what we're going to look at first, and that says take the partial derivative with respect to v of energy, and that from our rules is saying momentum. So we're talking about the time derivative of momentum, which we also know is force. So that's good. This is another way to get from the energy box to the force box. Alright, so the first one is going this way, and the second one is going this way. And in both cases you end up in the force box.